Welcome to this explainer. Today we're going to talk about those massive metal power line towers you see stretching across the landscape. And specifically, we're diving into the unsung heroes that keep their incredibly dangerous cargo safely up in the air. We literally see these towers all the time on our commutes or road trips, right? But most of us never really stop to consider the sheer engineering brilliance required to make them actually work. It's a wildly fascinating subject, so let's just jump right in.
Okay, let's start by imagining a truly catastrophic scenario. What if all that raw electrical energy coursing through those overhead wires just flowed straight down the metal towers and into the earth? Well, it would be a complete disaster. We wouldn't just lose our electricity, those towers would become instantly highly lethal. Just to give you an idea of the stakes here, an electrical arc can reach temperatures of up to 35,000 degrees Fahrenheit. That is roughly 4 times hotter than the surface of the sun. So how exactly do thousands upon thousands of volts cross the entire country without frying the ground? The answer actually lies in a remarkably clever piece of technology that quietly does its job 24/7. Here is our roadmap for today. We'll cover wrangling high-voltage power, the 2 life-saving jobs these devices perform, heavyweight suspension strings, extreme tension in substations, and finally, the modern polymer revolution.
Section 1. Wrangling high-voltage power and the physical stakes involved.
Before we even get into the electricity flowing through the system, we really have to understand the brutal physical realities that overhead power lines face every single day. The sheer mechanical strain is just immense. Think about the literal physical weight of thick copper or aluminum cables stretching for miles and miles. Now add the severe environmental stress they endure on top of that. They're constantly getting battered by strong gale force winds. And during the winter, thick layers of ice accumulate on them, which adds an exponential amount of weight. The structures holding these wires up have to be incredibly robust just to fight gravity and the weather alone.
And that brings us to our key term, the insulator. An insulator is basically a device that prevents high-voltage electrical current from leaking or short-circuiting out of the wire and flowing straight down the supporting tower. If an insulator fails, the power simply doesn't reach its destination, causing massive outages. But even worse, those metal towers themselves become deadly electrocution hazards. Insulators are the ultimate barrier between our civilization and raw, untamed electrical power.
Section 2. 2 life-saving jobs, isolation and support.
You can kind of think of insulators as VIP bodyguards for the power grid, and they're working 2 completely different jobs at the exact same time. First up, we have electrical isolation. They absolutely must prevent that high-voltage current from escaping to the ground, keeping the power completely and securely contained to the wire. But on the flip side, they also have to provide mechanical support. They can't just be a barrier. They have to physically carry, suspend, and secure these heavy, high-tension wires high up in the air, maintaining a safe distance from the ground. It's a really delicate balancing act of providing high-strength physical support alongside absolute electrical resistance. Section 3. The heavyweight suspension strings and how we scale up. So, as our power needs grow, the engineering obviously has to adapt to handle much larger electrical loads, and 33 kilovolts represents a major threshold in power transmission. Historically, engineers just used simple pin-type insulators for power lines, but once a line exceeds that 33 kV mark, those standard pin insulators become dangerously bulky and just completely uneconomical to produce and maintain. The physics of those higher voltages simply demand a totally different approach to keep the electricity isolated safely. We needed a better way to scale up. To blast past that 33 kV limit, engineers designed suspension insulators. The assembly is surprisingly simple, but it's totally ingenious. Step 1. You connect multiple porcelain or toughened glass insulator discs in a series. Step 2. You link them all together with metal joints to form this flexible hanging string. And finally, step 3, you suspend the really heavy conductor wire from the very bottom of this string, so it hangs vertically straight down from the tower arm, holding the live wire safely away from the metal structure. The absolute genius of this design, though, lies in its modularity. Because the string is made of individual discs, you get this incredible flexibility. Let's say lightning strikes, or a bird causes damage to just one single disc. Maintenance crews can go up and replace just that one broken piece without having to scrap the entire expensive unit. Plus, you can easily scale up your voltage capacity just by extending the string. A massive 132 kilovolt line will simply have a longer string with more discs compared to a 66 kilovolt line. It's just brilliantly efficient. Section 4. Extreme tension and substations specialized hardware. Sometimes physical geography forces engineers to use entirely different configurations. I mean, a power line can't always just go straight, right?
When a transmission line reaches a dead end, has to turn a really sharp corner to avoid a mountain, or needs to cross a massive gap like a wide river or a valley, the mechanical tension pulling on that line is absolutely staggering. Standard vertical suspension strings would swing wildly out of control or just snap entirely. So to handle this extreme physical pull, engineers use what are called strain insulators. These are essentially the exact same as suspension insulators, but they're pulled taut and configured horizontally rather than hanging down vertically. They absorb that extreme horizontal tension while still isolating the power.
Meanwhile, the hardware changes all over again when the power finally reaches its destination. Inside those high-voltage electrical substations, where power is routed and stepped down for your home, we use post insulators. Now, these might look a bit like traditional insulators, but they are incredibly robust. Unlike the flexible strings swinging in the wind we just talked about, post insulators are designed to provide rigid, unwavering support for massive, heavy equipment like bus bars and switchgear. They basically keep the live substation equipment locked safely in place.
And of course, we can't forget the classic workhorse of our local neighborhoods. For those lower distribution voltages, the ones operating under that critical 33 kV limit we talked about earlier, the good old pin insulator remains incredibly common. These are structurally much simpler. The conductor wire simply passes through a designated groove right at the top of the insulator and is tied down. They are structurally practical, economical, and highly effective for local power distribution networks.
Section 5. The Modern Polymer Revolution and Upgrading the Grid.
For roughly a century, glass and porcelain totally ruled the grid. But today, they are rapidly being replaced by composite polymer insulators. These high-tech devices feature a central fiberglass rod that's covered by weather sheds made of silicone rubber or an epoxy polymer. And the advantages here are huge. First off, they're significantly lighter, which makes them way easier to transport and install. They are also naturally hydrophobic, meaning they literally repel water, which, as you can imagine, is a fantastic trait when you're trying to keep electricity from arcing in a rainstorm. They're highly resistant to vandalism and breakage. But maybe most importantly, they absolutely excel in highly polluted or coastal environments where built-up dirt and corrosive sea salt would normally cause electrical tracking and failure on those older porcelain models. So, bringing it all together, we really have an incredible ecosystem of specialized hardware at work here. You've got the flexible vertical strings of suspension insulators holding high voltages overhead. You've got the horizontal strain insulators tackling sharp corners and rivers. There are the rigid post insulators locking down heavy substation gear, modern composite insulators thriving in harsh coastal weather, and those classic pin insulators routing local power under 33 kilovolts. It literally takes this entire spectrum of devices, all working together flawlessly to keep our modern world powered.
And that brings us to the end of today's explainer. Honestly, now that you understand the immense hidden stakes of mechanical support and electrical isolation happening high above your head every single day, I hope you never look at those metal towers the same way again. Next time you're driving down the highway and you look up at a massive power line, what invisible battles against wind, ice, gravity, and raw electrical energy will you see? Think about the unsung heroes silently keeping the grid alive up there and stay curious. Thanks for learning with me today.